Good afternoon, everyone. My name is MS Deepak. I'm working as assistant professor in BMSIT Bangalore. Today we are about to see software application laboratory. In that, the application of Excel sheets in structural engineering design problems. So, in order to know about the design, first initially I will explain about a plan and which part of the plan I'm going to do for Excel. So this is a plan, residential plan for this particular building. I'm about to generate a one-way slab for this particular portion. Let's see here. I have given the layout of columns and beams with the centerline diagrams. In this, the slabs are indicated with different notations. Let us say S3. S3 is a typical one-way slab, and I am about to design one-way slab for this size using the Excel sheet, and how we can use the same Excel sheet for different one-way slabs. Now, let us open a Excel sheet, and this typical problem is similar to that we study in the theory book. So this is a design of one-way continuous RCC slab. So I have just repeated the full problem of one-way slab. First step, the ultimate stresses of concrete and steel are given. The ultimate stress of grade of concrete is taken as characteristic strength of concrete is taken as 20 Newton per mm square, and the yield stress of steel is taken as 415 Newton per mm square, assumed as 415 Newton per mm square, and the span in X and Y direction means our plan here. This particular slab S3, the spans, the center to center distance I have taken, that is 1.83 cross 5.11. Okay. For this particular plan, I'm about to do this one-way slab. So 1.83 cross 5 cross 5.11, that is span in X direction and span in Y direction. So when we apply the limit, basic limit Ly by Lx should be greater than 2 for a one-way slab. So Ly by Lx here is 2.79, which is greater than 2. So here the constants are 20 and 4.15. The variables are 1.83 and 5.11. The variables are all are given in white highlighted boxes. Now, second step is depth of the slab. So in order to find the depth of the slab, the important factor is the span in X direction or span in shorter direction. So the spacing between the beams, here I have considered only the center line, center to center distances. So the spacing between the beams L will stand for 1.83 meters or 1830 millimeters. For slab spanning in one direction, means in this particular slab it is spanning in one direction or one-way slab, and it is just continuous over the other slabs. The other end is discontinuous. For this condition, span by effective depth ratio is taken as 20. This can be seen in IS 456. In IS 456, this particular table is given, right? In that we can write it for simply supported one way and continuous one way. Since ours is a continuous one way, here I am giving the data as 26. I'm just giving the data as 26. So this is a constant. variable that you must take consider from the IS 456 2000 code book. Now the effective depth is 70.38 meter. Since it is very very slender, I'm going for next round of why this 100 mm. This is to match the other slabs. Since it is a practical slab, I'm matching it with other slabs, giving 100 mm, giving good workability space also. Now, if the effective depth is so much, 100 mm, then what will be the overall depth? As we all know, the clear cover is 20 mm for the slabs. So when we add 20 mm to 100 mm effective depth, we get the overall depth as 1.2 meters or 120 mm. Leave it. Now, Excel sheet, similar fashion, step 3, write all the inputs. What are all the inputs required? That is dead load of the slab and live load of the slab and the factored moments. So how to do this load calculation? We all know live load considered here is 3. We can also consider 2 since it is a residential building based upon IS 875 part 2. But since I'm assuming that for this building is consisting of G plus 3 buildings, G plus 3 floors, I'm taking this particular floor slab, first floor slab, as slightly heavier slab, that is live load as 3, and with constant for every meter. This one stands for every meter. Now, what is the dead load of the slab? Unit weight of the concrete into breadth of the slab into depth of the slab. You will get the dead load. And weight of churki, weight of weathering course. These will be applicable when you are using it for roofs. When we are using it for roofs, these weight of churki and weight of weathering course applies, and weight of plastering also applies. If not, if we are using tiles flooring, then these all constants if we add, we will get around 1.5. I am taking that rough finishes as 1.5 for every floor, means we are doing tiles flooring, so it is going to be roughly 1.5 as finishes. Now when total dead load is 4.5 and total live load is 3 and they are not factored loads, so I am using the factor of safety that to be multiplied to obtain the factored loads as 1.5 into dead load, 1.5 into live load based on limit states of design method. So I get what is my dead load and live load. Now, the factored moments and shear forces at critical sections, and you applying the textbook formula, how to calculate negative moment, how to calculate positive moment, and how to calculate the shear force based on the textbook formula. First, write the formula, and you can see here the function. I have given this formula inside this box, inside this Excel cell. In this Excel cell, I have given the formula. So the same formula can be used, right? You can check here. I have given the formula. So when you apply this function, you will get the answers. Every time we need not require to change the values or cross check the values. Once when we do it correctly from the top, only the variable data are sufficient. Now we get the maximum shear force also. Now the reinforcements at critical sections are needed. So the main reinforcement, right? Main reinforcement. First, I am checking whether the section is under reinforced, balanced section, or over reinforced section. We must design for under reinforced section, right? So that we can check it with codebook, annexure G. So let us go to annexure G. So in order to check whether it is under reinforced section, we are using the formulas applicable here, mu limitation formulas, right? First we are checking here, we are getting what is the mu limit and what is the maximum mu. Mu should be within the mu limit value. So when you are going to add these both moments, say 3.93 plus 3.39, it is not going to exceed your limiting moment. So it is less than your limiting moment, so it is a under reinforced section, right? This mu is the summation of dead load moment and live load moment. Now I'm using the basic formula. We can also use handbook SP16 to calculate the percentage stream, or we can generalize to this formula. I'm generalizing it to this formula, moment of resistance. So by applying this one formula, we can calculate. This is present in Annexure G, page number 96 of your IS 456 2000. Now, when we apply, this is the formula. Now, when we apply this formula, you are multiplying this AST term inside the bracket, so you are getting it as AST square. Fine, proper. The equation will be in the terms of AX square plus BX plus C plus D is equal to 0, or AX square plus BX plus C is equal to 0, or a constant value. Ax square plus bx plus c is equal to a constant value. Here it is mu. So since we are getting polynomial equation of degree 2, I am using very basic method. See here, earlier I am calculating these things. So I have to calculate the value of AST. When I get in AST square in equation terms, I have to calculate in terms of AST. So I am using the formula in the best way I know. That is b square minus 4ac by 2a. X is equal to plus or minus b square minus 4ac by 2a. So when I apply that formula, I am getting the equation. Got it? These terms I am using, it is simplification for x is equal to plus or minus square root of b square minus 4ac by 2a. Apply the basic mathematical formula and you will arrive what is your x, that is your AST. So I am taking the least one because higher order it is not going to be applicable. The least x, that is AST. I'm getting what is my AST value. So every time I need not require calculator to calculate this. Listen very carefully. I have implemented this formula 0.87 Fy into AST first. So how I'm getting my AST? It is here. And how do I get this? From here, right? That is square root of b square minus 4ac by 2a, right? So since it is a very narrow slab and a small slab, hardly 1.83 by 4.88 meters or 5 meters, I can use the least size of bar, that is 8 mm diabars. So the area of one bar, pi by 4 into d square. So the area of one bar, I'm getting it as so much. So the entire area for 1 meter of slab is 450.53. That is well above 111.57. It is satisfying. So I am providing a spacing of 200. So the actual AST is So the actual AST is for every meter it is 251.33. Okay, so now I'm providing 8 dia bars. That's a small mistake here. Now I provide 200 spacing. I'm getting so much. So what is the AST? Now I am providing it is 251.33. Now if I change the spacing, if I change the spacing say 100, it becomes 502. Actually AST is more. Now you can see there to 450 up to 450 you can provide slab spacing. Taking into consideration about the concrete relation, concrete integrity and holdability on the RCC platform, I am providing 200 spacing. Why 200 Why I am not going for 300 though the code provides 300 as the maximum limit of spacing for any two bars in a slab. This 200 is a normal foot size of a human being. So at time of concrete placement, when it increases more than that, there is high possibility during concrete placement, there is high possibility that the persons can walk on it and there will be excess pressure on the small area. If it is going beyond 300 then excess pressure in that small area where reinforcement is not present, so there is possibility of too many dents or it can even collapse. So I am limiting itself to 200 to the maximum 220 Imagine a person is standing in single foot and he is carrying some load. So based on that calculation, that practical aspect, I am providing 200 Now, the distribution reinforcement should not be less than 0.12 percentage of the gross section area. The code book gives the limit. So I'm assuming distribution bar size also as 8 and I can get the area of particular bar spacing required. I'm providing 200 spacing. I'm getting 251.33 square. So I am going to provide main reinforcement and distribution reinforcement with same size of bars, that is 8 dia at 200 center to center, both in x direction and in y direction. Now we are going to check for shear stress. Usually for slab element, the shear stress will be automatically satisfied. If not, also we can check for the shear stress for this one-way slab. So tau v, that is nominal shear stress, is equal to Vu by Bd. You know what is Vu, that is 0.6 of dead load and live load in that particular length. So you know what is your Vu, and divided by the cross section of the slab, that is width of 1 meter and depth of the slab, that is 0.1. So from the code book, when tau v is equal to so much, and tau v is equal to so much, what should be the k value for overall depth is given. So we can take that k value, and tau c can be calculated with table 19 in the code book. This is table 19 in the code book. I can show you here the code book. When we go to serviceability limit, you can find the shear strength of slab. And what is this k factor, shear strength of the slab? We have to multiply with the tau c, maximum shear stress of the slab, and that limitation can be obtained, design shear strength can be obtained using table 19. So since ours is M20 grade of concrete, nominal mix, and percentage steel provided is between this range 100 AST by BD. When you apply this formula, what is the provided AST? You know that we know the provided AST, that is here it is 251.33 provided AST divided by BD, and thereon when we interpolate here we are getting 0.28, 0.3 when we interpolate between 0.15 and 0.25 for percentage steel 100 AST by BD, we are getting it as 0.3, right? When we multiply with the K factor, since ours is 120 mm slab, K factor is 1.3, we are getting the maximum shear stress value. So we are checking for shear stress, it is okay. It is more than 0.12, hence it is okay. It is safe, the slab is safe. So now we have developed a single one-way slab sheet for this particular plan, okay, for this particular layout. Now in this layout there can be more one-way slabs, or in some other layouts there can be one-way slabs. Since we have developed a Excel sheet, now imagine a building is having a different dimension one-way slab. So I am considering one-way slab as 3 meter cross 7 meter. Slab is there. This is a typical one-way slab. I have just changed the data. And 7 meters. And I'm getting Ly by Lx value as 2.33. Now we have to just do the basics. Wherever the highlighted portion is there, those are all the variables. You must correctly select the variables. So here it is 3 mm. The short of span direction is 3000 mm. Now you can see I can assume it as continuous one-way slab, right? Or a simply supported one-way slab. Let us consider it as a simply supported one-way slab for a change. Consider it as simply supported one-way slab. Now the effective depth required is 150 mm, right? Where this simply supported one-way slab will be common, it usually comes to a common hall. Usually comes in a common hall, narrow hall, right? See the effective depth here required is 100 mm. Say imagine I'm providing 125. I'm providing 150 mm, that is the effective depth required. Along with that 20 mm is the cover, so I am providing to round it off to 175 mm, 155 mm as effective depth. Now I am getting the overall depth as 175 mm. Now we have to calculate the load. So the load will be calculated as such. You can see here, right? The finishes I am assuming it to be 1.5 only. So the dead load of the slab is increased, the live load of the slab is increased, the moment is increased, the factored moments are increased. Now the factored moment should be within the limit. My mu limit value is 66.31, and when I am going to add, or when I am going to check with the end span and center span moments. So why it is positive moment at the center span? It is a sagging moment. Why it is negative moment at the support side? It is a hogging moment, right? In the interior support. So it is less than, mu limit is much more than the bending moments. Here the governing factor is negative bending moment at the support, simple supports. Now I'm using the basic annexure G formula from IS 456. This particular formula I'm using to calculate your AST value. Since I know the moment applied to this section, moment of resistance required for this particular section. So when I do it, moment to be considered here is 12.43. So when I'm going to equate it, I'm getting the AST required as 229.16. Right now, the diameter of the bar I'm changing to 10 mm. That's all I'm doing. So the area of one bar is given. What is the spacing required is given. I'm just changing the spacing to 185 mm. Right, the provided AST changes, and you can see the percentage distribution reinforcement required is 210 mm square. So I'm changing this. This can be 8 mm or we can apply 10 mm. You can check here. I'm applying 200 mm spacing. Now I'm providing, say here, 10 mm dia bars at 185. Right? And 10 mm dia bars at 200. Easily I am getting every answer. Tau value also is calculated, and since it is more than 150 mm, 175 mm, I am multiplying this factor by 2. Okay. Maximum shear stress here is, it is 0.15, it is going to be 0.28. The tau c value is greater than tau v value, so the check for shear stress is also done. And you can see now we can use this entire Excel sheet for different one-way slabs for same building or for different building. So the Excel sheet may be look a little tedious for the first time to develop, but once when we develop, here I have shown it as complete book-wise problem. You can also reduce according to your convenience, and you can form a small size table which and all input should be given and what will be the output. That's all. You can develop an Excel sheet and you can thereby acquire your required steel for your RCC elements. This is for about one-way slab. Tomorrow we will see about two-way slab. Right? Kindly subscribe to our YouTube channel to watch more videos on structural applications laboratory, on Excel sheets and in software applications using STAD Pro. Thank you.